Okay, so let's start. Welcome to our guest lecture within our course Databases for Data Science. I have the great pleasure to have Vladimir Shemyakin, who obtained his Doctor of Science in Technology degree from Lappeenranta-Lahti University of Technology in 2020 and is now working as a senior data engineer at Cujo AI, and he will give us first-hand insights on database technologies for analytical processing. Thanks again, Vladimir, and take it away.
All right, thank you. Thank you very much for having me here. So the topic of today's lecture is going to be database technologies for analytical processing. And I would firstly like to start from introducing myself and the company, what we are doing. So as it was, previously mentioned, I got my doctoral degree from LIT in 2020. And I have been working as a senior data engineer in Cujo AI since 2022. So there is also my LinkedIn profile link. So if someone wants to connect, you're welcome to follow this. Then about the company. The Cujo AI provides solutions for device intelligence and network security for network operators. We are running in tens of millions homes, from where we collect some telemetry data from the home routers, which can be then used to understand better the landscape of the devices and train our machine learning models to better protect our customers. We'll be dealing with quite huge volumes of the data. That's why we have quite nice understanding and expertise is how to handle a huge amount of data and how to enable our data scientists and data analysts to perform their work better. That's like a few words about who we are. And now I'd like to briefly introduce what content of today's lecture is going to be about. So during this lecture, we're going to explore the differences between online transactional processing and online analytical processing systems, and also with the focus how they are applicable and used in the data science and analytics. We will also going to review some modern OLAP technologies, the way how to improve the performance of those systems. Then also have a brief look how we can use some of those tools, or how actually to bring OLAP tools locally. And I hope that that's by the end of the lecture, they're going to be understanding how to choose and optimize proper database technologies which would serve your analytical needs and workloads. But to begin with, I want to establish some like foundations. Probably it's my like definitions, and this can be quite familiar for quite many of you, but still we want to set some common grounds of what OLTP and OLAP is about and how they differ from each other. So let's firstly speak about OLTP, which stands for online transaction processing. And these systems are backbone of everyday business operations, and they designed to handle a high volume of simple, fast transactions. This is achieved by highly structured and normalized data formats, which ensures consistency and avoid duplications. These systems, they are very well optimized for intensive workloads with frequent transactions. Yeah, you can see you can think about some basic examples of when you put some order in an online store, then LTP system make sure that, that these orders are recorded under the hood. The inventory updated, and your payment is goes smoothly through the payment system. Yeah, since OLTP excels at handling this like transactional workload, they are not very well suited usually for the deep analytical queries. And this is where the OLAP systems serve their purpose. So OLAP stands for online analytical processing, and they are usually designed for deep complex analysis over large historical data. In these systems, the data usually are organized in the denormalized format for faster query execution. And what does it mean? It's usually can be organized in the this star or snowflake schema, where when the central fact table can be linked to multiple dimension table in star-like structure. And then, for instance, a snowflake schema is further extend this approach by linking subdimensions to those table, forming the structure which resembles the snowflake. So this OLAP system that they enables enable analyzing the trends, some structures in the data, segmentation, segmenting the customers, and they're not well designed for frequent updates of the data. So they are very well suitable for read-heavy workloads and complex queries. But yeah, a bit to overview and summarize what are the differences between those two paradigms. I'd like to represent some architectural differences table on the next slide, and let's look at this more into details. So I have like few features emphasized here in the table, and how they are like different, how this approach is different between OLTP databases. For instance, you can think about Postgres SQL or some OLAP systems or engines. First of all, usually OLTP databases, they come like all at once, meaning that the query agent is usually highly integrated together with the storage layer. That's why usually the scaling of OLTP system possible only like vertically, which can be quite expensive overall. While with OLAP approaches, the usually engine is separated from the storage. Moreover, the storage can be some external, for instance, Amazon Simple Storage Service S3 or HDFS, which stands for the Hadoop, the distributed file system. So yeah, there is clear separation of concerns between the executing the query and actually how the data or where the data is stored. Also, from the focus, yeah, as the name suggests, the focus are different in OLTP and OLAP systems, such that it's in OLTP the focus is on real-time transactions, while OLAP usually serves the analytical purposes. And one of the kind of core difference, and what is very important, is the way how the data stored physically. So that is in OLTP systems, the data usually stored in row-based format, meaning that that's like individual row stored one by one, which is ideal for transactional workloads. while in OLAP, the data is stored in a columnar format, and that actually enables quite a lot of cool features. And I will speak more detail about this one, but just to give an example that the columnar format can actually be better compressed because the similar values are stored together. And such architectural differences they impact performance and scalability, and it can be quite significant for data science to actually understand what are the difference. That's why the next slide is dedicated to see what are the challenges might be there with OLTP and how those challenges are resolved or addressed with OLAP approach. So yeah, challenges with OLTP systems. Usually analytic queries can be quite different from the usual operational ones, and the underlying engines, SQL engines, they usually not that well optimized for such kind of queries. And that's also lead to the problem that's if you try to run certain analytical queries on the operational database or production database, it actually might lead to contentions of resources, which means that your analytical queries can actually impact the responsiveness of the database and actually how the customers and users perceive your service. So it's usually not really good idea to run analytical queries on top of the operational database. Again, data format, we will return to this question multiple times during this lecture. The data format is very important. That's how the data stored and how then you run your analytical workloads on top of this one. There is a scale limitation, as I mentioned, that since usually OLTP systems, they come all at once. The scaling of the OLTP systems can be problematic. It can be expensive, and there are some even you can think about some hard limits when the volume of the data becomes so huge that it's not possible even to properly operate the transactional workloads. That's why it's a common practice to keep only the most up-to-date and recent transactions in the OLTP systems, while historical data can be moved like some other places. That's why performing the analysis, like historical analysis on the such data can be problematic. And OLAP comes with quite a few solutions for those problems, such as query optimization. Since there is a very drastic separation of concerns in OLAP systems, there are very tailored solutions for the query optimization. Query engines for OLAP can actually be more suitable for OLAP for the analytical workloads. Also, workload isolation is important here because usually in OLAP systems, OLAP tools are isolated from the operational workloads. That's why the performance and reliability of services are much better in that sense. Columnar efficiency, as I mentioned, since the data is stored in the columnar format, it's much much better and resource effective use of the data when, for instance, you have some database, some table with tens of columns, and you perform your analysis only on the subset of those columns with the columnar table format. You can read only the specific columns. But again, more detailed on this bit later. Then scale-out architecture, since there are those separational concerns when the query engine is usually separated from the storage layer, it's much easier to scale out even to petabyte of scale, because with these distributed systems or these distributed query engines, it's possible just to add more workers, executors to your OLAP system to address some high loads or actually high volume of data. And historical analysis, the way how the data usually is stored in OLAP systems, that's like recent data might be stored close to historical data, where historical data, the only difference might be that it's stored in more cost efficient tier of storage provider. It's still it's easy to read most recent and historical data together. So these are some like solution which OLAP provides, and all of those can be quite critical for different data science applications which are mentioned here. So I think with the clear need in the scalable solutions for analytics, let's have a closer look of what the current landscape of OLAP tools are out there and how they can be used for different data science scenarios. All right. So to begin with, I probably want to mention a few key trends which are currently present in industry. Yeah, I previously mentioned already that there is a strong separation of storage and compute engine. This allows better scalability, where the execution or actually compute part of the OLAP can be scaled separately from the storage one. SQL is kept being a universal query language, which is understood in all those different tools. Of course, there are usually some specific flavors in different tools, and there are maybe some some fine-tuning peculiarities between the specific tools you are using. But overall, the structure is similar, is quite well understood, and the fact that this language is used in industry in those kind of scenarios. That there is an ongoing increase in real-time analytics requests. That's why the different tools which address this real-time analytics are being developed and maintained intensively. And of course, with the growth of the machine learning needs, there is better and more smooth integration with different machine learning workflows. Yes, speaking about query engines in terms of OLAP tools, distributed engines play a significant role in that one. There are quite many open source solutions which provide these distributed capabilities, and some of those solutions are then packed by different cloud service providers to provide some managed and scalable analytical solutions with minimal setup. There are also some embedded engines which allow you to run those OLAP OLAP workflows locally, but of course there are some limitation to which level or what other data volume sizes are suitable for such embedded engines. And yeah, I'm gonna devote a brief section to this embedded or local OLAP tools in the end of the lecture. Also, the deployment model of the OLAP tools can be different. So some of them self-hosted, and also some of them cloud native, as I previously mentioned. Some of the cloud providers also gives possibility to use some of those services with minimal maintenance burden. Yes. So, but I think to use those tools effectively, it's really necessary to understand the common structure or actually understand the internal components of those tools and how those like query engines allows you to process queries at scale. So the typical structure of the distributed SQL engines consists of coordinator node, worker nodes, and connectors, where coordinator node acts as the orchestrator, which actually responsible to parse the query, to create execution plans, and then schedule and distribute the corresponding tasks between worker nodes. Then it actually sit and waits till the workers perform the submitted tasks, and then it actually aggregates the result from those workers into the final result. Then worker node's responsibility is actually to execute the portions of queries which were submitted from the coordinator node. They are able to process the data from various sources thanks to the connectors, and then they actually emit the intermediate results to the coordinator node, and worker nodes actually where the horizontal scalability are taking place with the distributed SQL engines. Then connectors, they are actually interface with the different storage media. They might be speaking to S3, HDFS, or even to traditional databases, because it's possible to refer to data from multiple sources. There are also some optimization comes together with those connectors. Those optimization can be also very source specific. And yeah, you can see how the actually usual flow of query execution comes. So the client submit the query to the coordinator node. Coordinator nodes actually figure out how to properly split this task into available worker resources. Then it's actually worker perform their tasks in parallel and return the results to the coordinator, where it aggregates those ones and return to the client. So this is like the common flow, quite like generalistic how the distributed SQL engines works. But even with this like very performant engines. Usually the performance really depends on how you store the data and how you organize this storage layer of the data. So that's why let's consider different optimization strategies and techniques which commonly used in OLAP systems. And first of all, some quick overview, and I will go into like more details for all of those key strategies. But overall, there are usually the proper format selection. As I mentioned, columnar format is always preferred for analytical purposes. Then there is the way how you actually organize the data to improve performance for the filtering. This is related to the partitioning and partition pruning. And then there is also the way how you organize the data within those partition to improve performance for sampling and join the data. And all those optimization strategies can actually boost the performance of different OLAP workloads to like 10, even 100 times with respect to like blindly implement these approaches. Moreover, it comes usually with the reduction of the costs by minimizing the data you need to scan and resources you need to compute this one. And also it enables actually interactive analysis on petabyte scale. Yeah, about when would you like to use some of those optimization techniques? And the answer is like, as for the data format, more or less always. So this is kind of foundation for all other optimizations. Then partitioning is, as I mentioned, it's usually related to the filtering. So you can speed up the filtering by establishing the proper partitioning schemas. And then the bucketing is to improve the performance of the joins on the large tables. I multiple time already mentioned that that's like major factor of OLAP is the way how the data stored and the columnar format for this. That's why let's have a closer look into the columnar file format and how do they implement it and behave. So the columnar file format, they pretty much store the data in columns instead of rows. And since in this way the similar data are stored like close to each other, actually together, this enables better compression possibilities. Also, as I briefly mentioned previously, when you are only interested in a certain subset of the columns to perform your analysis, it's very beneficial because you pretty much read the only data you are going to use. This is ideal for analytical workloads in such manner. For instance, if you would like to calculate some averages, I don't know, some for sales where you would have only like needed a region and some sale information in the column. You read only those couple of columns and you're good to go even on the really long historical data sets. And just to mention the two commonly used columnar formats, they are Apache Parquet, which has embedded schema, very well suitable for compressions. There are really nice internal compression algorithms there, and it supports also complex nested data. Moreover, there are really nice features about the Apache Parquet, where in the file structure there are headers which contain some minimal statistics on each column stored there. For instance, like minimal and maximum value of each columns. That's why, for instance, if some of your queries just interested in this statistics, there is no even need to read the actual data in the columns. All the data already present in the headers, and that's like speed the execution even more. And there is ORC also, this optimized row columnar file format, which is default file format in Hadoop Hive ecosystem, and it also has really nice internal features to speed up or improve performance of reading the columnar data. And here I just want to give the really simplistic and brief example what are the differences between the row storage and column storage. Imagine that you have the column with which you have the table which with 3 columns. And you would like to perform the analysis only on one of those columns. In the case of the raw storage format, you would still need to read the whole data set, while in the columnar format, you can read only single column, which is briefly like a third of the whole data set. And this might be a really a nice performance boost and enable you actually to have to perform those queries much more efficiently and yeah, cost efficiently as well. But beyond the file format, as I previously mentioned, it's also important how you actually partition or distribute the data. That's why let's actually consider partition and partition pruning techniques. What partitioning is pretty much the idea that you divide your data into smaller logical segments. How you divide the data is usually based on the frequently filtered columns you're using in your analysis. And some example of this partitioning might be date time partitioning. So for instance, you organize your data in the folders with year, month, day, and then your partitioning become the files in those folders. And why does it matter? Because those query engines, they are smart enough to figure out based on the query you submitted that some of the partitions are not going to be used, and they pretty much mean that this data is not even scanned, and which might actually reduce the scan data by the order of magnitudes. And there are definitely some best practices how to properly choose the partitioning schema. So yeah, first of all, it's usually those columns which are frequently used in the where clause. But then there are some, of course, peculiarities about it that you don't really want to over partition your data. Just imagine that you are interested in some average statistics or average statistics over the week. That's why ideally you probably would organize your data storage that's stored by date, and you would like probably to avoid the our partition because it just brings extra small files. And why too many small files is the bad idea here is because it can deteriorate the performance of the queries when the underlying like physical storage can actually be overwhelmed with the amount of input-output operations, and it's kind of become a bottleneck. That's why it's usually a good idea to keep the proper balance between the granularity of partition you are selecting. And yeah, also the cardinality should be taken into account. That's why you probably wouldn't like to partition your data based on the certain column with really high number of unique values. But then there is other technique for actually to make the join more efficient and actually make the sampling possible from the large data set. And here where the bucketing comes into the stage, and let's discuss what it is about and how it works. So bucketing is pretty much organizing the data within the partition, and how it's done. It's usually done based on the column which you want to bucket upon. So the data is distributed between the fixed amount of files or buckets based on the hash value of that column which is you're defining. And that actually creates more homogeneous or actually more evenly distributed data set, and this has a lot of benefits, such as it enables optimized joins on the bigger data sets, enable like better parallelism because there is no so-called like hot partitions. The sampling can be done more efficiently because the data is distributed more evenly. And there is also better or consistent performance because there is no much skew in the data, regardless of what was the actual initial value distribution of specific columns. And some example like why it matters that you can imagine that you try to join some like large tables with this user ID. So it's good idea to actually firstly bucket your data sets by this user ID, and then actually the query engine is smart enough when it try to figure out what should be the execution plan. It might then it actually distribute the data between the workers. So that's the data for the same user ID are collocated on the workers, and there is no unnecessary network transfers between different workers. So that can be quite beneficial. But speaking about all of those performance optimizations and distributed systems, I'd like to emphasize that sometimes you don't really want actually to deal with all those distributed systems. Sometimes you have the task with which it's possible to like prototype or figure out some proof of concept on your local machine. And there are sometimes some local OLAP tools which actually enables you to do so. So let's consider what are the idea, what are the differences between local and distributed OLAP system, and I give also some example of such local tools. When and why? It is pretty much straightforward. It's can be quite obvious that distributed lab systems, they are have with quite high maintenance and provision costs. So there is usually infrastructure to set up and maintain. Then it's usually might be like overkill for more simple use case. That's why there are local tools actually which offer simplicity and without any drawback with the performance. And this enables data science to perform some prototyping or iteration over some maybe sample of the bigger data set. And that's quite can be quite convenient. And one of the widely used local OLAP tool is DuckDB, which has really bleeding edge optimization under the hood. That is like a vectorized query execution, which takes the best of the modern processors to parallelize certain executions. It has native support for quite many data formats, such as previously mentioned Parquet and all others like CSV, JSON. And it has a really nice integration with quite many tools which used by data scientists and data analysts. But of course, there are limitations. First of all, of course, it's not suitable for very large data sets. So some rule of thumb is under 100 gigabyte of uncompressed data, or something which ideally can be fit into RAM memory of your laptop or your machine. Then it's ideal for as I mentioned, for some rapid prototyping and analytical queries, and to learn certain SQL concept and teaching as well. But for production or enterprise use, there are some limitations on the concurrency, how the distributed processing is not possible at the moment, and there are some lack of some best practices from security standpoint. But as far as I know, DuckDB is really actively developed nowadays, so some of those limitations might be overcome in the nearest future. So I guess that's was more or less it about the lecture content. Let's have some key takeaways from the lecture, and then we probably can proceed to Q&A section. So, key takeaways I like you to have from these lectures is that there are OLTP and OLAP systems. They different systems. They serve different goals, and you need to make the proper tools. You need to use the proper tools for the for proper problem you have. Front of you. Then from the OLAP perspective, it's really important how you organize your data and how you store the data. That's where the columnar format plays a significant role, which can drastically increase the compression of the data you stored and also improve the performance of the queries and workloads. Then we covered also that's the way how you organize the data on the disk or on the storage is important. This partitioning and partition pruning are effective techniques for this one. Then the bucketing, another technique actually to further boost performance in the scenario where you need to join a lot of large tables. Then of course you need really to select tools which better suits your purposes. That's why quite often you would like to start probably from some local OLAP tools, and this is where the DuckDB, for instance, can be useful. And then you can look into distributed engines and how they deployed or provided as a service in some different cloud service providers. And last but not the least, all of those peculiarities about how you organize the data and all those optimization techniques can be really beneficial for the data science. They actually enable faster iterative analysis and feature engineering even on the data set, which otherwise would probably overwhelm individual laptop or machines. And that's, I guess, key takeaways from the lecture. And thank you very much for your attention. So now I guess the time for